Welcome back. In this video we're going to talk about a new way of constructing groups from old ones. This one is a very direct way of doing it, and essentially we take some number of groups and we just glue them together, forming a new group by just taking one element of each group as the elements. So this type of thing is called an external direct product. So let's dive straight in to our definition. So here it is, the external direct product of groups G1 through to Gn, and we just write it as G1 plus G2 up to Gn, where we put a circle around our plus. It's just defined to be a tuple, an n tuple. That's just like a list of n things in order, where we choose one element from each of the groups. Okay, so element Gi is a member of group big Gi. Okay, so this thing is itself a group. And the group operation for this group is just, you combine individual elements by their respective group operations. So that is itself a group, where the group operation on the ith element is the group operation of Gi. Okay, so it's pretty easy to verify that they form a group that way. So if you take two elements, you just need to make sure you know which group each one comes from, and to combine them together to compose two elements, then you just use the respective group operation there. And the order of the group, the number of elements in the group, is just the product of the individual orders of the individual subgroups, or individual groups. So G1 times the order of G2 up to times the order of Gn. That's only if each has a finite order. Alright, so that's our concept. So let's just test it out straight away with an example, just to see how this works. So we'll work with some Z groups. So I'm going to look at the external direct product of Z2 with Z3. So first off, we'll just list out all the elements. So we just take one from Z2 and one from Z3. So I'm just going to go 0, 0. I'll vary the Z3 ones first. And then the same 3 with 1 instead. Okay, so Z2 plus Z3 has 6 elements in it. Alright, so hopefully it's fairly clear that it's abelian, because each of the subgroups, or each of the groups making it up, are themselves abelian. This is abelian of order 6. So we might be interested in knowing what type of group this is. Remember, a group of order 6 has got to be isomorphic to either Z6 or D3 by our theorem of groups of order 2p for prime p. So let's figure out which one it is. Easiest thing to do is to look at various elements and see if they might be generators, because our suspicion might be that this group is actually cyclic. So consider the element 1, 1. If we take 0 of it, we get 0, 0. If we take 1 of it, we add 1 and 1 to both numbers. If we add 1, 1 again, we will get 0 in the first position and 2 in the second. If we continue on this way, 3, add another 1, 1, we'll get 1, 0. Notice that the second one cycles back to 0 slower than the first position. Then we'll get 0, 1. If we take 5 of it, we'll get 1, 2. And then finally, if I go one further, I'll get back to 0, 0. So hence, 1, 1 is a generator of our group, Z2 plus Z3, and it is cyclic and isomorphic to Z6. Alright, so with our groups of order 2p, when we did that one before. It was a little bit unsatisfactory because it didn't include the case where p equals 2. We specified that p had to be greater than 2, which meant we had to start at 6. So we haven't yet classified groups of order 4, and it turns out that using these external direct products actually gives us a means of being able to do this. So let's consider that one next. Okay, so a group of order 4, if we start listing out the elements, the first one is the identity, then we'll list out 2 other elements, A and B, which are not the identity and distinct from each other, and then by closure, the final element must be AB. Okay, so this is our stand-in for any group of order 4. And if it's, this could be a cyclic group, right? So if G is cyclic, then it must be isomorphic to Z4. Okay, so we're going to get rid of that case up front, and we'll consider the case where our G is not cyclic. Otherwise, its non-identity elements must have order 2. Why is that? Well, by Lagrange's theorem, all elements have to have either order 1, 2, or 4, because these are the divisors of 4, and we've explicitly excluded the case where we have elements of order 4, so every non-identity element must have order 2. Okay, so the order of A equals the order of B equals the order of AB, which must all equal 2. Okay, it turns out we can make a direct product of Z2 with itself that actually does the same thing. So we can construct an isomorphism to Z2 plus Z2. And what does it look like? Well, we'll map E onto 0, 0. Identity has to map to identity. And then a natural mapping was A goes to 1, 0. B goes to 1, 1. And AB, which will be A plus B in our right-hand side notation. So B goes to 0, 1, not 1, 1. AB will be A plus B, which will be 1, 1. Okay, so this is an isomorphism. It's very easy to check. I'm not even going to do that now. So any group of order 4 must be isomorphic to either this or Z4. It is isomorphic to Z4 if it's cyclic, or to this group here, which is the external product of Z2 with itself. Okay, that's quite nice. So now we have classified groups of order 4 also, just to add to our list of completed groups. Okay, so now we've sort of built the general idea. We know how to construct these groups and how to do the group operation. We need some of the basic tools. So we need, for example, to figure out what the order of an element in our external direct product group is. So it turns out that's actually quite straightforward. If we have the orders of the individual elements that make up our tuple, then the order of the element of the direct product is just the LCM of those elements. So let's see if we can go about proving that. So first off, we'll just create some shortcuts so we don't have to keep writing out that big long string of letters all the time. So we'll let S be the LCM of those things. So this is the thing that we're trying to show that the order is equal to. And we'll also let T be the order itself. And so we want to show that S and T are the same thing. So first off, let's just take G, our element, to the power of S. So here is our element here. I'm going to take it to the power of S. Now, just by the way that the group is constructed, we just take each individual element to the power of S within its respective group. Okay, but S is a multiple of the order of each one of these elements, so that has just got to be the identity, the identity, the identity, as S is a multiple of the order of gi for all the i's. Okay, so what we've shown, that if we take that element to the power of S, we get the identity, which means that the actual order is definitely no larger than this. So T is less than or equal to S. Right, so let's now take T equal to, if we take each of these things to the T, well, T is by definition the order of this element, so that also equals the identity of each thing. So this should be E1, E2, I guess. I should have labeled them before as well. Let's fix that previous one. E1, E2, up to En. Okay, because T is the order of my element, if I take it to the power of T, which means taking each individual thing to the power of T, I have to get the identity, otherwise T would not be the order. But that implies that T, if I take something to the power of T and get the identity, then that must be a multiple of the order of that element. That means that T is a common multiple of each of the orders. Which means that T will be greater than or equal to S. And thus, those two inequalities put together implies that T equals S, which is what we wanted. Okay, so now we know how to calculate the order of an element. We just need to have figured out the orders of the individual components of our element, and then we take the LCM of the whole lot, and that gives us the order of the element inside the product group. So let's test this out on an example. So we're going to look for all of the elements of order 5, or let's count how many there are, elements of order 5 in Z25 plus Z5. So we're taking our big group to be Z25 plus Z5. We're going to look for elements of order 5. Okay, so these will look like, what will they look like? Well, the LCM of the two elements will have to be 5. So what we're going to look for, elements of the form AB with the LCM of their orders equaling 5. Okay, so there aren't actually all that many possibilities there. If we have the LCM of the two being 5, sorry about that, then there aren't that many possible options for the order of A and the order of B. So possibilities are, so let's just make a little table, shall we? The order of A and the order of B. And let's look for different options. So one possibility is that A could have order 5 and B could have order 1. Then the LCM of order of A, order of B will definitely be 5. Similarly, we could have both of them being elements of order 5, or we could have one being an element of order, A being an element of order 1 and B being an element of order 5. Okay, so let's give these cases some names. This can be case 1, 2, and 3. All right, so let's just see what possible elements we have. So elements of Z25 of order, so we need to know how many there are of order 5. Let's see. Elements of order 5, these will be 5, 10, 15, and 20. Okay, so in elements of order 1, well, there's only 1. just be the identity. Likewise, we can do the elements of Z5. We need to know how many, this is the B's. We need to know elements of order 1 and elements of order 5. So elements of order 5, there are not many. There are 1, 2, 3, and 4. And elements of order B with order 1, again, is just the identity. Just in case you had forgotten how to do that first part here, when I did this one, elements of Z25 of order 5, I took one of them, 5, because 5 is an element of order 5, and then I just did GCD of the order, which is 5, with K equals 1, and I found all those K's, and then I did 5 times K. This is back to our cyclic group theorems. So elements of Z25 of order 5, that means we've got our element of order 5 and we want to find other elements of the same order. Okay, so we have our possibilities. We have 4 elements of Z25 of order 5. We have 1 of order 1. And similarly in Z5 we also have all 4 elements of order 5 and 1 of order 1. So if we go through our cases now, in case 1, there are 4 possibilities. So remember, case 1, we have to choose an element of order 5 from Z25 for A and an element of order 1. So there are 4 choices for our A and there's 1 choice for our B. So there's 4 possibilities. Then for case 2, there are 4 possible choices of A that have order 5. There are 4 possible choices of B that have order 5, so there are 16 possibilities here. And for the third case, there's only 1 choice of A that has order 1. There are 4 choices of B that has order 5, and so there are 4 possibilities here. So overall, if we combine those all together, there are 24 totals. Adding 4 plus 16 plus 4, there are 24 elements of order 5. In our external direct product group. And if you wanted to list them all, you just do the appropriate choices from the sets we created before. Alright, so for our next example, we're going to try and find the number of subgroups of order 10. There's not the number of elements this time, the number of subgroups of order 10 in Z100 plus Z25. So a similar kind of problem, except this time instead of finding elements, we're trying to find subgroups. So we should expect that it's similar kind of process, but we're going to have to adjust our attack slightly to make sure we get the number of subgroups, not the number of elements. So first we'll actually find the number of elements of order 10, and then we will figure out how many subgroups there must be. So first, find out how many elements of order 10. Okay, so we're looking for A, B, where the LCM of the order of A and the order of B is equal to 10. Alright, so let's just use Lagrange's theorem to figure out what possible orders elements can have, and then we can figure out what combinations will give us an LCM of 10. So elements of Z100 can have orders. Let me just list off the factors. 1, 2, 4, 5, 10. There's not much point going further, but we can. 20, 25, 50, and 100. And elements of Z25 can have orders, well, 1, 5, and 25. Not so many options. Alright, so if we want to make this similar table to what we did before, we'll do order of A and order of B And we want to find combinations that give us a least common multiple of 10. So, if we were choosing something from our first list here, and we're choosing something from our second list here. So our first one, if the order of A is 2, we can choose 2 from the first set and 5 from the second. The LCM of 2 and 5 is definitely 10, so that's one possibility. Another possibility. What about if we choose an element of order 5 from Z100? Well, that doesn't work because there's nothing in Z25 that will give us an LCM of 10 with that, so we can't actually have an element of order 5. So the next possibility is an element of order 10 from Z100 and an element of order 1 from Z25. They're both in both sets, that's fine. Any others? There is in fact one other option, and it's taking elements of order 10 from our first set and elements of order 5 from our second. All three cases here will have LCM of the two orders equal 10. All right. Z100. We're going to do the same kind of thing we did before. Has one element of order 2. So we only need to know about 2 and 10. Right, and that is 50. And how many elements of order 10? Well, elements of order 10, well, there are 10, and then we take the GCD of 10 with k equals 1. There are 4 elements of order 10. And these are namely 10 is our first generator, and then if we take the numbers relatively prime to 10, there are 1, 3, 7, and 9. So it'll be 10, 30, 70, and 90 will be our 4 elements of order 10. Okay, and in Z25, we need to know elements of order 1 and elements of order 5. There's one element of order 1, and that is just the identity. And elements of order 5, we did that in our previous problem. There are 4 elements of order 5. These are 5, 10, 15, and 20, like we did just before. All right, so let's go through our cases again and figure them all out. So case 1, there are, so an element of order 2, there's only one of those, and there are 4 elements of order 5. So there is 1 times 4 equals 16 of these. Equals 4. All right, now case number 2, there are 4 possible elements of order 10, 1 possible element of order 1. So again, there's 4 possibilities here as well. Case number 3, this is looking very similar to our previous one. There are 4 elements of order 10, 4 elements of order 5, so there are 16 possibilities here. So overall, again, we just add those all up. There are 4 plus 4 plus 16 equals 24 elements of order 10. Okay, so if we're just looking for how many elements of order 10 there were, then we'd be done. There are 24. However, the question is actually asking us how many subgroups of order 10 there are. In fact, what it should have been asking us was how many cyclic subgroups there are. That's a very important distinction. So how many cyclic subgroups are there of order 10 in this group? Well, let's find out. Every cyclic subgroup of order 10 has 4 generators. Remember we had that thing that said this thing is equal to a to the k if and only if GCD of 10 and k equals 1. So we're applying, again, our cyclic subgroup theorems from a while ago. And no two subgroups have an element of order 10 in common, because if they did, it would generate both of them. Right? If both subgroups had an element of order 10 that they shared, then that element would have to generate both. So in those two subgroups of order 10, we should be saying here, it would generate both of them, so that can't be. Therefore, each one of these subgroups has 4 of its own elements of order 10. Okay, and that is our set of 24 things. So we have overall 24 divided by 4. Okay, because each of those 24 elements of order 10 we have, 4 of them generate each of the subgroups we have. So we have 24 divided by 4 equals 6 subgroups of order 10, cyclic subgroups. Of order 10 in Z100 plus Z25. All right, so now we've got a bit of a sense for how these things work. We first define what one of these groups was, and we talked about how its group operation was simply just the group operations of each individual component of our direct product. Likewise, inverses are just inverses of each individual element, etc., etc. And then we figured out that the order of elements, which is something that we need to be able to do, is just the LCM of the orders of the individual components of an element. And we showed that we can use that idea together with some counting arguments to figure out how many elements of different orders, or how many cyclic subgroups of different orders we have in various groups. So we'll call it a day for this video, and we'll catch you up on the next one. So I'll see you then.